Hello, my name is Roy Simpson, and I am a professor of mathematics at Columbus River College in Sacramento, California. This is a video for integral calculus students who are pretty much in the first 2 weeks of their integral calculus class. And in this video, we'll prove a theorem that derives or gives us the volume of a rotational solid found from using cylindrical shells, or as I say in class, rings. You'll also notice here that I use a lot of complicated variables. I use lambdas instead of x's, and I use etas instead of y's. The reason why I do that is because you don't know which axis or whether you're rotating about a vertical or horizontal line, and so I like to keep things as general as possible. This formula works for pretty much anything. Before we begin, let's go ahead and visualize what we're talking about, because a visual is always great to start with. Now let's suppose we have some function here, and I'll just use traditional function notation and call this f, and it is a function of x here. And we want to rotate this function out into your space beyond your screen, back into the screen and back behind the screen, and come right back to this. So we have this three-dimensional rotation coming out. There are a couple options. One option you learned so far likely is the disk or washer method, where you place in plates that are horizontal here, and they rotate around and create circular disks. That is not going to work very well here, because our function f of x, to find, maybe I should back up and say it's not going to work very well, because to find the outer and inner radius of that rotation, this left side, or right side, sorry, and this left side of the rotation, they're both defined by the same exact function. And that makes it pretty difficult, if not impossible, to therefore do the washer or the disk method, whatever you want to call that. Stacking plates is not going to work very well, because your outer function is the same as your inner function. So when you do the subtraction, you run the risk of having zeros for your areas. That's not going to work out. So instead, we invent a new method here. And the new method just requires a slicing in the other dimension perpendicular to that slice. Let me go ahead and draw in a nice pretty slice here. I'll just get a nice sizable slice right in there. And of course you see that slice has a width to it, a little dx, and in fact that width, really, if I want to be exact here, it's a delta x, because I could see that width. Once I cannot see it, it's a dx. But then what I'm going to do is I'm going to rotate it all the way around, and that'll create a nice ring. Let me see if I could draw that for us. Okay, I think that's pretty good, considering that I can't see what I'm drawing as I'm drawing it. So that's as good as it'll get. Any of my students who have me as an instructor, they know that I'm not the best artist in the world. But this gives you an idea, right? That's just a ring, like what you would wear on a finger or something like that. So we are going to discuss how to find the volume of just that ring. And then we're going to add up a bunch of those volumes. We'll just keep stacking them side by side, widening this ring out. Well, we'll start at A, and then we'll widen it out until we have all the rings stacked all the way to B. Okay, so we want a representative ring. We want to find the volume of that representative ring. So let's go back to the theorem here. Now, the first thing I should probably do is rewrite this in a language that maybe most students can understand here. So I'm just going to replace some of this wording in here so you can believe that we're talking about the same thing. So in this case, instead of eta equals h of lambda, I'll just say that we have some y value that is a function of x. I'll still call it h of x, because I like that letter h for this theorem. And then we're going to allow x to go from A to B. So x equals A to x equals B. And of course that changes this entire integral here, just the look of it at least. So we're integrating from x equals A to x equals B of 2 pi, and it has something like r of lambda. Our lambda here is x. So r of x, so it's some function of x, times h of x dx. So we're going to derive this theorem here, where x is defined to be the axis perpendicular to the axis of rotation. There you go. Okay. All right. So first thing we're going to do is look at that representative slice, and we're going to build up the volume of that, like I said before. So let's hop back. And if you look at this ring here, if we want to measure the distance around, because that's going to obviously be part of our measurement for the volume of this ring, we need the distance around. Well, the distance around that ring is just going to be its circumference. So we happen to know the circumference of a ring, circumference, which I cannot seem to write very well right now, is normally 2 pi times its radius. I'll write in the word radius here because I'm already kind of using the word r. So that would normally be the circumference of a ring. But if we only find the circumference, that's like saying we have a wire that we've wrapped around and we know the length of that wire. We still need to know the height of this ring. So the height, well, in this case, we happen to know that that height is a function of wherever we are evaluating this ring at, or in other words, some representative chunk there. So I'll call this x sub I star because this slice, as we all know from integrals, starts at x sub I minus 1 and ends at x sub I. So we call that the ith slice. It's an interval from x sub I minus 1 to x sub I. And we are going to pick a random point, which we'll find out in a moment is not so random, but we'll pick a random point called x sub I star. Okay. And in a moment, I actually want to replace all these letters with something a little bit better. But anyhow, we want to know what the height is at that representative point, and that height will be just h evaluated at x sub I star. Okay. So that's pretty good. So far, we're pretty okay. By the way, I should replace this with h just so that we keep our language all the same. And let's see. So we have a circumference. We have a height. Well, circumference is just a linear distance. Height is a linear distance. So linear distance times linear distance will be distance squared. That will be an area. We still need another dimension to make a volume. Well, something we didn't account for here is the thickness. This thickness, this delta x. Okay. And here's where my lettering is going to slightly change because I'm not a big fan of the x's here and all that fun stuff. I usually like to use r's for the radius, but I'll still use delta x here, and then I'll start writing language in a moment. But I happen to know that the width of this ring, to give it a volume, is just some delta x. Okay, so let's go ahead and write that down first. So I happen to know the volume of the ith slice here, the ith ring, if you will, is just going to be 2 pi times the radius of the rotation. So I'll just write that down and we'll kind of work our way out of that. And times the height of the ring at that point, x sub I star. It's a horrible star there. And then times the width at that point, which we'll call delta x. All right, so far so good. Now there's something, if you've ever read a calculus book, or maybe you've had a calculus teacher, or you currently have a calculus teacher that proves this slightly differently, it's because I'm using kind of a logical derivation of it. Well, maybe I should say a more conceptual derivation. I'm using the fact that we already know calculus, really. I'll talk about the volume approach to finding the formula in a moment. But first, we'll just do this conceptual approach because I like this conceptual approach. It works well for me. One thing we need to do here is we need to find out what the radius is. Now, this is why in the original, let me hop back here, in this guy right here, this formula, my theorem just says 2 pi times a r function, a function r of x. That r of x is the radius function. And I don't like to write down that it's 2 pi x because it's not always going to be 2 pi x. It's only 2 pi x if you happen to be rotating around the y-axis and there are no shifts, right? So in this case that we're looking at right now, if I were to draw out the actual radius from the center of that ring to the edge here, that distance actually is x. But imagine if we shifted this whole situation. In other words, instead of rotating around the y-axis, we want to rotate around x equals -1. Then if I wrote down that the volume of the ith slice is always 2 pi x, that would be absolutely wrong. It's always 2 pi times the radius from that ring, the edge ring, to the center, the axis of rotation. So just keep that in mind when you see in a calculus book that they might have an X here. Also, I have a video on how to find the radius for rotational volumes. You should watch that because really right now we have the entire theorem right in front of us. We're pretty much done. So you're just going to, maybe I'll say that this is equal to 2 pi. And of course the radius just depends upon the slice that we're looking at it. So I'll call it r sub I, and I'll say h of x sub I star, delta x. And now to find the total volume, I'm going to roughly sum up a bunch of these, right? From I equals 1 to n. So I take n rings here and stack them. And each of them has a volume, 2 pi r sub I, h of x sub I star delta x, right? This is the Riemann sum, and it's just saying 2 pi r, circumference, times height times width, so that's the volume. And of course, if you take the limit as n goes to infinity, the true volume is just equal to that limit, if that limit exists and approaches infinity, of that horribleness. Let me just go ahead and scratch it out here. I equals 1 to n, 2 pi r sub I, which is dependent, by the way, on x. I'm just not writing that in there. H of x sub I star delta x. And of course, this turns into the integral from where you start to where you end. So a to b of 2 pi r of x, h of x, dx. Okay. Now, and that is actually our theorem. That's exactly what we're talking about. It doesn't have to be x; it could be y's. Okay, so the way I originally wrote the theorem with lambdas kind of shows you that you just replace the letter with whatever you want. But let me go ahead and just kind of be a little more rigorous, even though this is pretty rigorous here. Let me just show you what your instructor may have been trying to convince you of when they did this whole derivation, which I think is a little bit much. I think that my derivation is perfectly fine, but let's go ahead and look at how most textbooks, authors, and instructors would do it. Yeah, I think I got that cleaned up pretty well. So what most of them do is they say, okay, listen, we don't know calculus, or we know very little about calculus. So we can only use stuff that we knew prior to entering into a calculus course. Specifically, I know how to find the volume of simple solids. So I could look at this ring and say, you know what, the volume of that ith ring is equal to the outer volume, right? So in other words, the volume, if I were just to have the outer shell and shade everything in it, that solid volume, minus the volume of the inner. So I'm erasing the inner volume. So essentially, you start with a solid cylinder and you bore out the center, and that gives you that ring. This is how they mostly start this derivation for that ith slice. Now we happen to know that the volume of a cylinder. So let me just write that over here. The volume of a cylinder is equal to let me get my pen working here, pi r squared. That's the surface area of a circle, and then h, or the area of a circle, times h. And that'll give us the full volume of a cylinder. So we happen to have two cylinders, an outer cylinder, and then we're boring out or erasing the inner cylinder. So I'm going to use the words outer and inner quite often here. In fact, maybe I'll use O and I. Well, no, I already have the letter I. Oh, that sucks. Okay, so the volume of the outer. Well, let's take a look here. If I look at this distance that I'm kind of marking up right here, I'll call that radius outer. And this distance on the inside, I will think of something very creative. I'll call that radius inner. So at this point, I have an inner radius and I have an outer radius, and that'll help me define the volume of this bored out cylinder. Let's go ahead and write that down. This is pi r sub outer squared h minus pi r sub inner squared h. Each of those terms has something in common, a pi and an h, so I'll just factor those out because there's no reason to leave those there. So pi h, and then I have r outer, gosh, I wish I would have used 0 or something like that, squared minus r inner squared. Oh, well, that's kind of fancy. That's a difference of squares. I'm just going to use some old school algebra here, and I'll write this as a difference of squares. It's just r outer minus r inner. That pause was me debating whether I want to continue to write r outer and r inner. But I guess I am going to continue. If this goes off the screen, I'm just writing the word inner here. Okay. Well, we get to this point and we just kind of go, okay. So is there some type of weird relationship I can create? What is geometrically r outer minus r inner? Well, it's the distance between the outer radius and the inner radius. Oh, well, that's kind of nice, because if you think about that, r outer minus r inner, that's the distance between the outer edge here and the inner edge. In other words, that's a delta r. Well, hey, that's pretty fancy. So let's go ahead and just say that's pi h times a delta r, and then we still have r outer plus an r inner. Let's see what else we could do. Well, let's see. I happen to know I want this to be 2 pi out front. So let me go ahead and grab this business right here. And I'll say that's equal to 2 pi. Because I know that in my theorem I need a 2 pi. So I guess I'm heading there. 2 pi h delta r. And of course, if I throw a 2 pi in front, or a 2 in front, I will have to offset that by dividing by 2. So what I'm going to do is something like this. R outer plus r inner divided by 2. Okay, so you see that 2 over 2, that'll cancel and get us right back to the last step. And if you take a look at this, actually r outer plus r inner over 2, geometrically, or maybe mathematically, what does that mean? It's the average of the outer and inner radius. By saying the average of the outer and inner radius, I'm saying it was really smack dab in the center of that wiggle right there. It's right down the line here. That's the average radius. So, okay, that's just my average radius for this wiggle. So let me go ahead and write that in. This is the same thing as saying 2 pi h delta r times, and then I'll just call this business here r sub I. Might as well. I'll just say that's the average radius for that ith slice. So times, that was, by the way, it's supposed to be an h there. 2 pi h delta r. And then let's go ahead and say this is times r sub I, which is the radius, this business right there. If I write it in the proper order, it'll be 2 pi r sub I h delta r. Now, if you compare that to the proof that I just did, where I said it was 2 pi r times a height times delta x, right? It's the same exact argument. And you sum up all these volumes and you get the same stupid thing. So either way, it'll give you the same exact volume, or the same exact integral for the volume. So you can go either way here. One way I think is very kind of natural to go with. The other one is using a little more pre-algebra, right? Volumes of cylinders. And there is a little bit in here that you have to think about as you do this version of the proof, because a lot of people would stop maybe at this point where they have the pi h times r outer squared minus r inner squared, and then maybe doing a difference of squares. Once they get that difference of squares, unless they're really, they've worked in calculus for a while, or they're pretty astute, they may miss the fact that the outer radius minus the inner radius, that's just a delta r. They may miss the fact that, they may look at this and just go, I'm done now, rather than noticing, hey, if I divide that sum of radii by 2, I'll get the average radius, and I can throw the offsetting 2 out front. It's just some kind of creative mathematics involved in this version of the proof. Either way it works, and I'm okay with either.